Okay, so let's, we'll go ahead and work these two. So rank the water solubility here. So we'll just rank them 1 to 4 from most, say most water soluble to least water soluble. So what's going to confer water solubility is the ability to hydrogen bond with water. Molecules that have more of an ability to hydrogen bond will be more soluble because they have more interactions, favorable interactions with water. I know we didn't talk in lecture about the solvation sphere yet, but I think you've read about that or trying to apply it. So now we're looking at not the forces between each individual, the same or like molecules, but now what's the interaction with water? And a rule of thumb in general is that if you have a polar functional group, like an alcohol or carboxylic acid or a ketone, that if you have one polar functional group for every 5 carbons, it will be water soluble. Now, so there's like a kind of a cutoff point, water soluble versus not water soluble. Here we're asking you to rank, okay? So it's going to go towards which can better bind to, interact with water. And so some of them will fall on one side and some of them will fall on the other, okay? All right, so take this one. So butane has no polar functional groups, so is it going to be water soluble? No. So it's not water, let's just say no. We'll come back to ranking. All right, here's a 3-carbon ether. Is this going to be water soluble? Yes. It's going to be marginal, but ethers are it's a polar functional group, meets the criteria anyway. So we think it would maybe weakly water soluble.
Weak, yes.
Yeah. Now I'm thinking diethyl ether is, you put another carbon here and it's definitely not, well, okay. It will form 2 layers with water, but it is to some degree soluble. Okay. I'm thinking out loud. We'll say yes. Okay, it's got 1 polar functional group for every 5 carbons. 3-carbon alcohol. Yes. Absolutely, right? Yes. And then here's another. No. All right. So now, water solubility. We've got 2 yeses and we got 2 no's. So if we rank that, let's rank these 2. So which one can form or interact with water better?
C.
C. Okay, but let's think about why. So if I draw this out, this ether, it can hydrogen bond with water, right? It has 2 acceptors, so it could form up to 2 hydrogen bonds as acceptors. This one can hydrogen bond with water as well, but it can donate to form a hydrogen bond, and it has 2 acceptors. So it could form up to 3 hydrogen bonds at any given time with both acceptors and donors. So OH group is definitely going to be the most water soluble. So all of the factors are pretty much equal. There's 4 big atoms, 4 carbons, 3 carbons and an oxygen, same here, and then 4 carbons. So it's they're about the same, roughly the same size. Okay, so the second one must be the ether, right? Because it's water soluble, and these other 2 we would say are not. Now, water solubility is really, there's no, just like with pKa's, right? It's really, we can say not water soluble. It's not appreciably water soluble, but there is a difference in the solubility of these. One would go into water a little bit better. Okay, and so what do you guys think? A. Why would you say D?
Like A is like a line, it's kind of like big. D is more like, to me, seems more like smaller in terms of.
It's going to be more compact.
Wouldn't that be
Well,
bottom?
What's that?
I just think like longer end up chain, it's going to be easier to, I guess, break apart or something if it is to be dissolved in water.
Okay, so to break these apart, good question, good point. So if you had a drop of this, and it's going to either dissolve in water or not,
Yeah.
means that water has to pull it apart from other like molecules. So this one is being held together by what forces? Van der Waals. Well, what about this one? Van der Waals. Which one has more binds better to itself? Does this one have stronger bonding to itself compared to this one?
Yes.
Why? This has more surface area to interact with other molecules. So there's more height. If the boiling points of these, this would have a higher boiling point than this. This has a lower boiling point. I think that also would play a role in its water solubility. So if you have these, they're going to dissociate a little bit better easily. They're going to come out of, and because they're more compact, I think there's less. What actually happens in the water is that it orders the water. I think there's less ordering per molecule of this than there's this because it's just a tighter, more compact molecule. I think that's why. But this should, I think, should be 3, and this should be 4. So I think distinguishing between A and D probably goes towards which one of those has a higher boiling point. I don't think. I forgot to turn this on, did I? No. I don't think it's that critical, in my opinion, that you distinguish between the water solubility between A and D. I don't think that's that critical. But I do want you to be able to distinguish between which of these has a higher boiling point, right? So which one has a higher boiling point? A, which means it has more intermolecular bonding, right? Okay, labeling nucleophilic sites and electrophilic sites. Okay, so here we're just looking for nucleophilic sites, partial negative charge, and unshared electrons or pi electrons, right? Really, and there's some well, you'll see an exception here. So bases and nucleophiles, unshared electrons or pi electrons. Bases and nucleophiles are going to be neutral or negatively charged. Okay, so that's really what you're looking for. A neutral, negatively charged molecule that's got unshared electrons and pi electrons. All right, so let's go here. Where are the nucleophilic sites, or the nucleophilic site here? Okay, definitely on the oxygens, unshared electrons. Okay, and so we can say that's nucleophilic. Okay, anything else? The pi bonds. Okay, so the pi bonds, we can also label those as nucleophilic. Now, a benzene ring has special stability that makes it not very reactive, but when it does react, it usually does react as a nucleophile. Okay, so it definitely is a nucleophilic site.
Is it all the pi bonds?
Well, there's not really, it's resonance stabilized, but then there's another, it also has another property called aromaticity. So the pi bond, it's really not a pi bond here, there, and there. It's actually partial bonds all the way around.
Okay.
But electrons in the ring can react as a nucleophile. Yeah.
I was going to say, if you have a nucleophile site, you have to have an electrophile site for a molecule. Yeah?
No?
No.
No?
Oh,
Okay, so what about where's the electrophilic site? Okay, we'll call this the electrophilic site, right? The hydrogen. And, you could have said, because this is a partial positive charge, and you could say this, I'd be okay with you saying that's an electrophilic site. It's not quite. Well, actually, there are some cases where that carbon is electrophilic. So, those are the places that have partial positive charge. Okay, so it's different than the Lewis acid. It's got to have, the Lewis acid has to have polarized bond hydrogen or low energy orbital. Okay, what about this guy? What are the electrophilic sites here?
Oh, I might translate. Carbon on the end.
This one?
Yeah.
Why?
Because the pi bond is negative. Partial negative.
Well, there's, you know, there's no formal charge here. Okay, the difference between the electronegativity of these carbons is very little. No, you know, they're the same. There is a difference in electronegativity between these two, but because a sp2 hybridized carbon is a little bit more electronegative than a sp3, but not much. So there's not. So these are all nonpolar bonds.
Would it be because there's just hydrogens at the end, so you can just pull one off and add electrons to it?
It's not very acidic. Yeah. So I would just say there's no electrophilic site. The most acidic hydrogens, though, the most acidic hydrogens would be these guys, because if you pulled one off, these electrons could go here, and those electrons, you could draw resonance for those. But I would say no electrophilic site here. And then the nucleophilic site, pi bond. Okay. What about for acetone? Okay, so we draw the all the unshared electrons, right? I didn't draw them in for you. If you don't draw them in, then you may miss that that's a nucleophilic site, right? So nucleophilic site, and you know, consistent with that, it's got a partial negative charge, and here it's got a partial positive charge on that carbon. Okay, so where's the electrophilic site? Right there, on that carbon. Okay, and that's a really important electrophilic site that we'll study a lot. Okay, and then for we have this molecule already.
For going back, would it be on this pi bond for the nucleophilic site? Right there, yeah.
Yeah, you know, yes and no. Okay, here's why. There's a resonance form for that. So these electrons can go up to there.
Yeah.
You can rearrange them. So the resonance form looks like this. Okay, so those, in other words, those electrons aren't, you know, they're not just there, they're around the oxygen. You know, they're, to say that the pi bond is nucleophilic is really the same thing as saying the oxygen is nucleophilic, right? Because when you consider these. Yeah.
So if we're looking at an alkyne, would the triple bonds be a nucleophile or would it not?
I'm sorry, for
An
a,
alkyne.
yes. Okay, so let's say you had this. An alkyne. Where's the electrophilic site? None. Where's the nucleophilic site? Pi bond, yeah. Good. Okay, and now this guy here? There's a partial negative charge there, so this is the nucleophilic site. And does the lithium, would that be an electrophilic site? Yeah, I guess. Okay, so recognizing these things is important. Now, as we move forward, what we'll find out is it's the nucleophilic property of this that's important, and we're not interested in that. Later on, we'll figure that out. But right now, if you can identify these things, you're starting to look at the molecule in the ways that will help you predict their reactivity. Same here. So this site is nucleophilic. That site's electrophilic. The thing that dominates carbonyls, ketones, aldehydes, carboxylic acids, and esters and all that, is the electrophilic nature of that carbon. So this one doesn't come into play too much, very little. But it doesn't matter right now, just recognize what you're doing is looking and trying to identify where those areas of positive, partial positive, where are the areas of partial negative. Where the, with partial positive charge, do I have unshared electrons? And do I have a pi electron? So that you can define bases and you can find nucleophiles. For the electrophiles, the electrophilic area is just partial positive charge, which is a little different than identifying a Lewis acid, right? They're not exactly the same, okay? What's going to be far more important as we move along is the idea of electrophiles. We'll keep using the idea of the Lewis acid, but electrophiles would be by far the more important concept.